Okay, I had some students ask for a worked out problem using the Arrhenius equation. So I'm actually going to work out, this is the last problem that we did in class today. And this is one example of what we can do. Basically in this equation there's a whole bunch of stuff like rate constants and activation energy and temperatures that you might be given, and one of them is going to be the thing that you're going to end up solving for. Frequently, you use this to solve for the activation energy, but in this case, we'll actually be solving for the final temperature. So let's see what the question tells us. It says a hypothetical reaction has an activation energy of 15 kilojoules per mole. So we know that the activation energy is 15 kilojoules or 15,000 joules per mole. And then they ask us at what temperature, so temperature is the thing that we're going to be solving for, will the rate be 100 times faster than it is at room temperature? Okay, so now we've got these pairs, T1, K1, which is our first pair of temperature and rate constant, and T2, K2, which is our second pair of temperature and rate constant. So our first temperature we said was 298 Kelvin. Our second temperature is what we're going to be solving for. And now they didn't really tell me what the rate constant is, but they did tell me it's 100 times faster. So I'm just going to say that it's 1 and 100. I can do this because whatever the value of the rate constant is, if it's 100 times as much when I take the ratio like I'm going to do in the equation, it's going to end up canceling out all the rest of it. So the 100 is the only thing that's going to be left. So now I'm going to take all this information and I'm going to plug it into my Arrhenius equation. So I have the log of K2 over K1, which is 100 over 1, equals the negative activation energy, 15,000 joules per mole, divided by R, 8.314 joules per mole Kelvin, times 1 over T2 minus 1 over T1. T1 we know is 298. Okay, so now at this point, what I'm going to do is I'm going to actually take all these things that have numbers and I'm going to find numbers for them because right now it's a little bit too complicated for me to deal with the algebra. So I'm going to use my calculator. I will hold it here. Look how fun that is. There's my calculator, and I'm going to take the natural log of 100. That's my thing on the left, so I'll write that down, 4.6052. It's generally a good practice to just leave a few extra decimal places there. Okay, and then this equals negative 15,000 divided by 8.314. So that's going to give me negative 1804.2. And what am I left with here is actually Kelvin, because the joules per mole cancel out and the Kelvin comes up to the top. And then I have 1 over T2. I still don't know that, but I do have 1 over 298, and that is 0.003356. Okay, so now thinking about what I have to do algebraically, I've got this stuff over here and it's multiplied by this number, which is inconvenient because I want it to be, my T2 to be by itself, so I'm going to actually divide both sides by negative 1804. So I've got 4.6052, which was what I had there originally, divided by negative 1804.2. And that's going to give me on the left side negative 0.002552 per Kelvin. And that's going to equal, now our parentheses can be undone, 1 over T2 minus 0.003356, which again is per Kelvin. And now I've got this thing over here and I don't like it because it's messing with my T2. So I'm going to add this to both sides. So I take my negative 0.002552 and I'm going to add 0.003356. And now over here, I'm going to have positive 0.0008035, and this is again per Kelvin. And this equals 1 over T2. To find T2, I take the reciprocal of both sides. So I'll use my 1 over x button, and I get 1245 Kelvin for my second temperature. The biggest challenges here, two places where people are going to make mistakes, are first, not being able to identify the information that they've given you in the problem. I find it's always really useful to just make a list somewhere of everything that they've told me. And another thing is sometimes people don't associate the temperatures and rate constants correctly. So for example, it would have been wrong if I said it was 298 and that was 100 times faster. So watch out that you're associating those two pairs correctly. Other than that, it's really an algebra issue. Just take your time and be careful and you'll be fine. So there you are. That is the Arrhenius equation.